Hi, this is a physics lesson covering sections 5 and 6 in chapter 21 of your textbooks. And this will be our last lesson on magnetism. And this is going to be a quick study on how the right-hand rule that we learned yesterday with establishing the force of a charged particle going through a magnetic field, the direction that the force sends that particle was explained with a right-hand rule. We're going to explain how our Earth is saved on a daily basis because of our right hand, okay? And it's no slight to you, Eric, being a lefty. We'll actually introduce, you can use a left-handed model for this if you want. Before we do that, I just want to touch on something I forgot to mention in yesterday's lesson. So I was talking about how the kinetic theory of matter works into the concept of magnetism, how all the elementary particles that make up matter are constantly in motion, they're vibrating, okay? And that motion, because they all have a charge to them, the elementary particles, they have a motion, they establish a magnetic field, and they can orient themselves in certain domains. They can align themselves all in the same direction if the material is the proper material, that it can be affected by a magnetic field, or that it can establish a magnetic field on its own. And I said, if that motion is not strong enough to overcome the force of the magnetic field, the material retains its magnetic properties. Okay, if the kinetic motion is so great that it's greater in energy than the magnetic force, the magnetic field within the material, okay, it loses its magnetic properties, or it doesn't gain them, or it may be induced with them when a magnet is brought by, but once that magnetic force is removed, okay, the energy of the motion takes over, and the particles, the atomic particles align themselves in a more random motion instead of aligning themselves magnetically, okay? And with that, that means, and we studied in when we delved into heat a little bit, okay, the more we increase the temperature of an object, the more it gains kinetic energy at the elementary particle level. So the more kinetic energy it has with an increase in temperature, that means the less likely the material is going to gain magnetic properties if a magnet is brought near. Or it's more likely if a material has magnetic properties on its own, it will lose them as the temperature increases and increases and increases. And they brought that up in the last part of your section for reading yesterday, what they called the Curie temperature, after Madame Curie and her husband, that if once a material gets so hot, a magnetic material will lose its magnetic properties because it's too hot. There's too much kinetic motion at the elementary particle level. The elementary particles will not align themselves in magnetic fashion, north poles to south poles, all those little bitty particles lined up in the same direction. And so that's what happens. And then the inverse, the closer we get to absolute zero, which theoretically is where all that tiny little motion stops, okay, if that were to happen, there's no kinetic energy, okay, and so the magnetic properties of the material will rule the day. And in fact, a material that is magnetic is most efficient. It will create the most force from its magnetic field the colder it gets, the closer and closer it gets to absolute zero. So that's kind of an aspect, of that domain model of magnetism, how it relates to the kinetic energy theory of matter that we discussed and how they both can kind of confirm each other in that case. Okay, so right now, just a quick, I would have you read through those sections in the book, as well as make sure you read the facets of physics on the paleomagnetism and the age of the Earth on page 462 and 463. They're pretty easy reads. They're pretty interesting, and the questions that you'll need to answer in your homeworks are pretty self-evident in those readings. I'll just draw attention to a couple aspects. The declination chart at the top of page 460, that's something that we had to deal with on a daily basis in the Coast Guard, knowing where you are in the globe, because we navigated by true north, not by magnetic north. How do we do that? Well, we set up gyroscopes on ships. We get them spinning super fast. Okay, once you get something spinning super fast on an axis pointed in a direction, okay, Newton's law of inertia, okay, Newton's law says that body will continue spinning in that manner. It will keep aligned to true north, okay, as long as it keeps spinning at then what we do, we energize those gyroscopes to keep them spinning several thousand revolutions per minute, okay? They go super fast. But we have magnetic compasses on the ship for backup in case, we lose power or we lose gyroscopes do go bad once in a while, okay? So we had to have those charts handy there. We also had to know the annual variation because they don't update those charts, but I think about every 10 years or so, 10 or 15 years. So the book indicates the magnetic pole is moving around a lot on the order of 40 kilometers per year, okay? So it's moving around quite a bit. Another thing to keep, why does that chart look so weird? Why isn't it more uniform as far as, if the magnetic pole is off kilter, the axis of the magnetic pole is off kilter from the axis of the rotation of the Earth? Why does that chart look so complicated then, that the variation from magnetic north to true north varies so much? Well, you look at that model of the Earth's magnetic core on that facet of physics on page 462, and you'll see it is not a uniform looking iron core, a molten iron core that the Earth has. It's rather irregular looking, okay? It has bulges in certain areas and it has voids in other areas, okay? That's why that chart is looking so weird. So just a couple aspects to point out there. But really what I wanted to point out here is how our right-hand rule, and I'm going to be referring to that on page 465 of your textbooks if you want to open that up, so you can apply this right-hand rule. So we've said in that lesson yesterday, okay, the force of a charged particle moving through a magnetic field, and we said, remember, a force is only introduced if a charged particle is moving. If there's a charged particle there and it's not moving, there's no force on it, okay? We need to have velocity, okay, of that charged particle. The force of that particle moving through a magnetic field is dependent on the quantity of charge, the velocity of the charge, the B, strength of the magnetic field, okay, and the angle at which that velocity vector and the magnetic field interact, okay, the vectors for those. So let's just look at this here with the sun, and what we have here is a giant solar flare, and the sun is sending out radiation and solar flares and eruptions all the time, okay? And we've noticed on your textbook drawings, and the Earth has a magnetic field, and I've drawn one in. It's kind of a lumpy shaped one, but a simple one, but useful nonetheless. And we're going to use our right hand rule, and our right hand rule says, okay, we make our right hand like a gun, and we point that other finger out, our second finger, the middle finger, 90 degrees to that. So we got something like this, okay? So what do? We align this finger, the index finger, with the direction of the magnetic field. We notice the direction of the magnetic field proceeds out of the magnetic south pole, which is the geographic north pole, okay, points downward. The arrows, the vectors, point downward and proceed in to the north pole, the magnetic north pole, which is at the geographic south pole, okay? So our index finger will be pointing down in the right-hand rule. Our thumb indicates the velocity of the charged particle moving through the magnetic field, okay? That is going to be our solar flare. And remember, when we studied states of matter, we didn't get into too much the fourth state of matter, okay? We studied gas, we studied liquid, we studied solids and how they reacted and interacted with that kinetic theory of matter. We didn't study the fourth one, plasma, okay? And we said plasma is a fluid, okay? And its main characteristic is highly ionized, highly charged particles, okay? So what we have here, we have coming from a sun when it erupts, okay, it sends plasma out. What is plasma? It is a fluid consisting of highly ionized particles. That means lots of plus charges and lots of minus charges. And I have really big Q's here because there's lots of them, okay? And it acts like a fluid, okay? And they're headed directly at Earth, straight at Earth, okay? When it interacts, that magnetic field, okay, our right-hand rule, okay, the magnetic field is pointing down, okay? The charged particle is headed this way. I've got it aligned. Here's my charged particle. Here's my magnetic field. My third finger is doing what? It's pointing straight out of the board. And in the book will say they indicate that in a vector with a circle with a point in the middle, as if the point of an arrow were coming right at between your forehead, right in between your eyes, okay? And so what does that show us? In the case of solar eruptions, plasma headed to the Earth, highly ionized particles, and we're talking like energized stuff that would fry us if it hit us directly. Okay, it would burn everything to a crisp on Earth. There probably would not even be bacteria that could survive it. What happens when it hits the magnetic field, okay, because the charge is big, because the velocity is big, this is plasma going at a significant quantity of the speed of light, okay? When it hits our magnetic field, and especially when it hits it square on at a 90-degree angle here, okay, what happens? Bingo, it gets deflected around the Earth. It comes around this. Now remember, this model applied to positive charges, okay? So that applies to those big positive ionized particles, okay? They get deflected around the Earth out of the chalkboard. Well, what about the negative ones? Well, the negative ones, we can use the right-hand rule. They get deflected the opposite way. Or, Eric, if you want to use your left hand, do the same thing with the left hand and see which way it points. It points into the board, and they indicate that as a vector like this with an X in the middle to indicate an arrow going into the board, and we see the tail end feathers of that arrow from a bow and arrow, okay? So it's going into the board for the negative charges. It's coming out of the board, and so what's happening as those charges come toward Earth, they go like this, around the Earth, and it saves us from getting fried every day. Each and every day, 24/7, 365 days a year, shows how your right hand saves the Earth from being destroyed by solar radiation, okay? So that's a very practical application, that right hand rule, and we're starting to see now the interaction of electric charge and magnetism and how they're starting to get joined at the hip. and how, in a very practical way, it's a good thing that God has created his universe that way, okay? And this is also the same concept, and we mentioned that in our electrical shop class, okay? This is the same concept that creates the spinning of motors in our industrialized, electrified society. Okay, it's the same concept, that right-hand rule. So I hope that can help bring home an important point of that. And this, again, we'll be concluding our section on magnetism next week. I'm not going to have a whole lot of homework sets as far as like math problems. It's going to be mainly theory, but we want to join these and show how more properly they join together in the electromagnetic theory of electricity, and how that's such a revolutionary discovery. It really is. It has transformed our culture here on Earth. It's the one thing I think that has brought us out of the Stone Age, I guess, the horse and buggy age, into a modern society, because we can pump electrical power long distances at relatively cheap costs, and because of this right-hand rule, we can have it do all kinds of work for us, and it's pretty cool. We'll get into a little bit of that next week. So have a good weekend. This should be an easy homework assignment for you to do. That's due on Monday. So long for now.